So this is another in the video series of how did a scientist become a psychic? It's really about more than that. It's really about how you can use this journey that I'm sharing with you to understand more about what is going on in the world and these highly nonlinear, confusing, chaotic times. How can you make more sense of it and transcend the boxes of logic that you might be trapped in, because I've been trapped there, I get it, that you might be trapped in, to see this from an elevated, a different perspective. So in this one, I want to talk about quantum mechanics. A lot of people throw around this term. Okay, so there's, on the scientific side, there's quantum mechanics and what people's relationship with it. And to many practicing scientists, my brother is one of those, many practicing scientists, they have a very specific view of what that is, of what quantum mechanics is and what it means. And then out in the personal development and spiritual side, there are many people who talk about quantum mechanics, often kind of anywhere from kind of accurately to quite inaccurately. They talk about quantum mechanics. So I want to talk about quantum mechanics from somebody who actually has a physics degree and whose brother is a physicist. I didn't pursue it into graduate school, but I think I know enough to talk a little bit about it, because my story starts in quantum mechanics in college. It was a senior course for the physics program that I was in, and we were required to take a year of quantum mechanics. And I remember arguing with my teacher multiple times, and they weren't just arguments where I was saying, no, you're wrong. They were arguments of, that doesn't make any sense, please explain that to me. And the physics teacher's answer was always, in essence, that's what the equations say. That's one of the equations that they teach there, is Schrodinger's equation. Schrodinger's equation is the equation that describes the wave function that so many quantum systems, well, all quantum systems, operate within. And it describes how those waves evolve over time and then ultimately collapse into a particle that then interacts with other particles, and then they start acting wave-like again. So I was like asking about especially this collapse, this moment when things look like this water does out here. They look all wavy. It's just a whole series of waves everywhere, spread out. They're distributed. They're not like a point, like a rock. If you look into this water, there are stones in there. There are particular points, stationary points. But the waves, they're all constantly moving and flowing around. I couldn't have planned this more perfectly, right? Sitting next to a place with little waves on it, little ripples on it. And I didn't plan it, but hey, serendipity is a real thing. So, it just bugged me. This idea that, okay, things are waves, and then they become particles, somehow, through what's called the collapse of the wave function, and then they later on become waves again. So one of the big explanations for that is they actually don't become particles until somebody makes a measurement or an observation. There's this famous, it's called the split light. There's a word for this that is escaping me right now. Too much information in there. Split interference experiment, whatever. You send a beam of light through two slits. And you send it through these two slits, and if you send a beam, like a wavelength, through the slits, because of the way the waves interfere with one another behind the two slits, because they come back together on the other side of the slits. And so they can interfere, and they create what's called an interference pattern, a pattern of ups and downs that indicates that, like, this wave collided with that wave and that made a smaller wave, but over here they added up and made a bigger wave and all of that. So there's an interference pattern. Okay, so that makes sense. A light is like waves, and so of course they're going to make an interference pattern if you split the beam and then they come back together. It makes sense, unless you send like one thing through at a time, one photon at a time. So a photon is the smallest little unit, the smallest little packet that you can have of light. And somehow, even if you send one photon at a time, what's interesting is when you measure on the other side of the slits, you will see that one photon, you will see it show up on your detector or your film. In the old days, it was like film that they used to detect X-ray film. So you will see that dot where that photon landed, or your detector will detect that photon. One spot, one place. Okay, great. All right, so you sent a single photon through, it went through one slit, landed in one place. Okay, do it again, do it again, do it again, do it again. It's like throwing a bunch of darts through the slits. And you would expect, okay, like you throw a bunch of darts and some go through one slit, some go through the other slit, and then you just get a pattern on the back side of that where, you know, there's kind of distribution near one slit and a distribution near the other slit, and that's that. But that's not what you get when you send one photon at a time that should only go through one slit at a time. You get a pattern after you look at many, many, many dots. They add up. They add up to that same interference pattern as if you had a whole bunch of light going through at the same time. How does that happen? What that means is somehow that one single thing is going through both slits at the same time. It's acting like a wave as it goes through the slit. Somehow there's interference happening, even though one thing at a time is going through. It goes through, it has this interference that determines where it's going to end up probabilistically. Now I know this is getting like heady, and I apologize, but bear with me, we're almost done. It's like saying that this thing is really a wave that's going through, and it's going through both slits, but then suddenly it acts like a particle when it lands on the detector. And this has been repeated again and again. This conundrum, this fundamental paradox that things, if you look at these individual quanta, whether it's an electron or other kinds of quarks that make up protons and neutrons, if you look at these things individually, they behave like waves until they interact or until they're measured. And I was scratching my head over this, and because my physics teacher would not answer this, he just said it's in the math, and I'm like, what? I want to understand it. I don't want you to just put an equation in my face and say, just believe the equation. That's a bunch of BS. An equation is just a model of something. That's all it is. It's not explanatory necessarily. Maybe to some people in some weird way it is, but not to me. So I asked a lot of questions, and over time it emerged. There are different theories about what is actually going on. One is the parallel worlds theory, saying that actually there are different parallel realities, and in one of those realities the photon went through one slit, and in the other reality the photon went through the other slit, following these wave-like patterns, that somehow these realities are controlled by waves. And so the photons went through one of these slits in different realities, and in our reality we only saw the photon landing in the one place. But if you add up all of the realities, that's the whole interference pattern, where you have all of the photons that went through in all of the different timelines. Okay, so that's one explanation. Another is that you have something special about the observer. The observer who says, yeah, okay, now I'm measuring this, and something about the interaction of our brains, our observation, our measurement with that system then causes that to collapse. So you may have heard about Schrodinger's cat. And Schrodinger's cat is all about this same thing. It's like, is the cat alive or dead, or is it in a superposition? What superposition means is it's a combination of both alive and dead. It's a wave that says it could be both at the same time. That's what waves do. And it's both at the same time until you like open up the box and measure and determine, is it alive or dead. So I don't suggest doing that with real cats, by the way, unless you're a very cruel person. So please don't. And so anyway, it's an interesting thought experiment. And the Schrodinger's cat kind of defies some of the things we know, because it's not like this happens just somehow randomly. So there was another thing I encountered later, and I'll talk about this book and this theory more. It's by Roger Penrose, and it's called The Emperor's New Mind. And it's a very heady, technical, he's a mathematician, and a very well-known mathematician. And he was trying to figure out consciousness. He was working with a guy named Stuart Hameroff, trying to figure out what is consciousness and where does it come from? Is it just really just the biological molecules bouncing off of one another in our brain, or is it something more? Is there more to it that even if we build the most advanced AI, that the AI is not going to do exactly the same thing that we can do? And their argument at the time, which I still believe, by the way, but their argument was that no, the brain is doing some unique things that computers can't or won't do until or unless they take advantage of certain quantum features. But just traditional computers won't be able to do certain things that we do. And so far, even with our most advanced AI, I'm still not seeing them proven wrong on this point. We'll see where it goes. Curiosity, right? But back to the quantum mechanics, what they argued is that it was quantum effects in the brain. It was the same superposition effect that gives our brain an interesting edge over the traditional computer, over the yes, it's yes or it's no, and it's only one way or the other. And that not only that, but that all these quantum systems, that there's this thing called quantum gravity, and when a quantum system gets to a certain threshold of bigness, that then it makes that decision to collapse the wave function, and that the wave becomes a particle temporarily. I still don't find that fully satisfactory for explaining it. But my point about all of this, there are many points, but I'll just try to stay focused and make one, is that our consciousness has potentially something to do with quantum mechanics. And this is really important because it's so dismissed in mainstream science. It's one of the things that just disgusted me, really honestly disgusted me, about being a faculty member at one of the premier, like a top 5 public university, R1 university, and having all curiosity about these kinds of things just shut down. I remember this was when I was a postdoctoral researcher years before I was a faculty member, and I remember going to somebody who was an expert in microtubules because Hameroff and Penrose, their theory was that if there's a quantum superposition, if there's this quantum wave weirdness going on in our brain, it might be happening in these structures called microtubules. These are little structures inside cells that look like tubes, a tubule. And they extend and contract, and biologically they do all sorts of things there are some hardcore biologists studying them and trying to model them and figure out how and why they do what they do, and they do some pretty amazing stuff, but not all of it has been explainable, even now, by biology. They were saying, Hameroff and Penrose were saying, that it's quantum effects in the microtubules, that our brain, each neuron, each tubulin protein inside the microtubule, inside the neuron, can actually exist for times in this superposition between two different states, like a yes state and a no state, and that these can act together in waves that interact over extended space in our brains and possibly even outside of our brains. That the collapse of the wave function into a specific yes, it's a yes, or no, it's a no state, that collapse has to do with interactions that are non-local. That's the key point of this, non-local. And that's why I brought up quantum mechanics in the first place, because all of the materialist thinking, all of the thinking that says, how could you possibly have a dream when you're in the Canadian wilderness about your dog dying and going away, and then your dog goes away, without explaining that just by randomness? And the way that can be explained is non-locality. And this is why people bring it into personal development and spiritual stuff, is this idea that it gives us the sense that there could be a deeper layer of connection here. And our current science is mostly ignoring this. There's a guy in Canada, Jack Tazinski, who's been researching this, and he's made progress. He hasn't had a lot of support and funding for this, but he has made progress. And more, like recently, he did a computing experiment that computed like what would happen in these microtubules if there's quantum stuff going on versus what if there's not quantum stuff going on, what's called classical. And it was really an interesting experiment that really pointed towards, for these to do what they need to do, it's quantum. And there have been other experiments out there. Like there was a big one published, I believe it was in Nature magazine, one of the preeminent scientific magazines, around 2007, that was showing that photosynthesis, the way that plants absorb light energy and then turn that energy into what's called ATP, which is the energy source of our cells. The way that they absorb that energy, they go through a two-step process. It's like a little dance. It's like a little two-step. Boom, absorb, boom, transfer. Because they have to first absorb, and then it sits here for a second on this part of the molecule, and then it has to be transferred over to the other part of the molecule. That energy, that little bit of energy that it absorbed, has to be transferred to the part of the molecule that then activates the ATP, that then turns that energy into something chemical. So it's a two-step dance. And what this paper showed is that, like, if you were waiting for a classical model, a traditional model, a mechanistic model of this photon would come in and it would sit there for like years before the random configuration would be appropriate for it then to transfer over how it needs to transfer over, that it can then go make ATP. A very long time, far too long for photosynthesis to actually work. They showed through this modeling that the only way that this process could happen on the time scale it happens is if there is something quantum going on, where the light comes in and then there's like a quantum coherence between the two different units that then transfers the unit of energy from that photon from the one unit to the other unit in this coherent way very rapidly. That's what they showed. They showed that there must be, or very likely, I shouldn't say must in science because you never know, but it seems very likely that you have to have something quantum, something non-local going on, and it's still very small space, but non-local happening for photosynthesis, which if there wasn't photosynthesis, none of us would be here. None of those trees out there would be there. Nothing would be here. Like at least nothing that looks like anything that we are used to, right? Photosynthesis, quantum mechanics. Now, when evolution, yes, I believe in evolution, although I think we've got some things about it wrong, but I think there is a process of evolution that happens biologically and mentally and culturally. I think evolution happens. Evolution is real. Evolutionarily, when biology finds something that works, it uses it more than once. It doesn't do it it's not, oh yeah, that was a really nice, efficient experiment. There was a really nice thing that I found. Oh wow, cool. Like that worked to do this quantum coherence thing and make photosynthesis work, but I'm gonna forget about that everywhere else in biology. I'm gonna just forget about that and not use that thing that worked again. No, biology, evolution reuses things that work. So for us to think that it doesn't happen like in our brains, these quantum effects, is ridiculous. After Penrose and Hamrath published their theory, published their book, there were so many skeptics pushing back, people stuck in their little temple of randomness, boxes of logic saying, no, that can't possibly be the truth, you're wrong, blah, blah, blah. There are all these arguments against them. And then back to my story, when I was a postdoctoral researcher, I had an opportunity to go after some funding to research this. I wanted to do some more modeling of this and figure out what was going on. There was a funding opportunity, and I went and talked to a faculty member who studied the microtubules, and he's, oh, no, no way. Just he dismissed it out of, he didn't even consider it. There was no consideration, there was no open-mindedness, there was just no curiosity whatsoever. He's like, I know what's going on, I know my biochemistry, I've been steeped in my biochemistry, and this is just wrong. Now, before you go say, okay, but aren't you being a bit harsh? No. Look up Daniel Shechtman on YouTube. Look up Daniel Shechtman and his story of winning the Nobel Prize for what are called quasi-crystals. Quasi-crystals are crystals that don't have regular even symmetry. They're like weird odd symmetries. That's why they're called quasi-crystals. When he first started discovering them, he was just doing experiments. This has nothing to do with quantum mechanics. It just shows you how conservative and stuck scientists often are. He was doing this research on quasi-crystals, well, just on regular crystals, but he kept getting these results that they didn't fit any of the models of regular crystals. And he's like, what is going on? And finally he's like, well, okay, so maybe there's something aperiodic going on here, or something not quite symmetrical going on here. And so he started playing with that, and he came up with a model that fit all of the data he had. So he goes to his mentor at the time, a senior guy. He was younger at the time. He goes to the senior guy, and the senior guy, the first thing the senior guy says is, go back and read the textbook. This can't be happening. Your data is wrong. There must be something wrong. And this is always what people say when they don't like your theory in science. Your data must be wrong. You must have done something wrong. There must be something wrong with your experiment or with your device, rather than actually considering, like, maybe their damn box of logic is wrong. Maybe they are stuck in a paradigm that's not actually true. And if you look at the history of science, there are so many places where we've been stuck in a paradigm, stuck in a box of logic, and then finally the evidence becomes incontrovertible. But for this quantum mechanics and consciousness thing, we're still not fully there yet, at least not on the scientific side. I think on the more consciousness side, the personal development side, there are a lot of people who are like, yeah, yay, quantum mechanics, but they don't really know what they're talking about. And so I just want to wrap this up by saying quantum mechanics is important, because my journey, like from not really understanding it to then learning about it and saying, hey, wait a second, that really doesn't make sense. There's something more going on here. To then starting to learn how this might connect to our consciousness and the amazing, miraculous things that our consciousness does, and also potentially explaining how I could have a dream in the remote wilderness that told me my dog died, a non-local event, and then my dog did die, thousands of miles away. It explains a lot of stuff. It opens interesting doors, and it comes from curiosity. It comes from that open-mindedness of just wanting to get real answers. And every person I know, I'll finish this, every person I know who's really gone on an open-minded quest of things has found a lot of unexpected stuff out there. I have a friend who he's on YouTube. His name is Simeon. He studies UFOs and now Bigfoot. And I've always been pretty skeptical, like when he talked about him. But it's just so interesting talking to him, because he's a statistician, PhD level statistician, who got into UFOs and Bigfoot. Another scientist who's gone down an interesting path of curiosity, led by curiosity. That's the number one thing. And he interviews people. He talks to people. He talks to people who've had these experiences with all these things. And I'll do a later video more about that. But the bottom line is that it's hard to dismiss all of the evidence, all of the stories, all of the occurrences. And he believes there's something going on. He doesn't say exactly what he thinks it is. He keeps an open mind, but there's some interesting stuff there. And so I'll end on that note, is just really trying to encourage keeping an open mind. That's been the core part of my journey, and that can help you bring new perspective on what is going on in our crazy world right now. New and perhaps better and even more optimistic perspective on what is going on that will help you get out of the box of logic and help you relate to this in a more positive way. Not saying that it's going to be pretty moving forward, but saying that there is reason for hope, reason for optimism. So I'll see you in the next video. Meanwhile, please like, please subscribe. And if you've if you're interested in quantum mechanics, if you have some experience with that, I'd love to hear from you in the comments and see what you have, what experiences you've had with that, even if you're not like a quantum mechanics student like I was. All right, I'll talk to you later. See ya.